Yes.
Used to stop you, but now
Sure.
it's past 5 in my time. Alessia, do you like to share screen and put
Yes.
your...
Okay. And here it is again. Let me minimize also.
Newborn, yes, very good.
Yes, I moved.
Maybe we can wait 1 minute to finish, but people can finish the conversation. But if not, we will.
No, but it's okay. Better to start the talk.
Okay, dear friends, today we have a big pleasure to have a talk by Alessia Platania. She will tell us about asymptotic safety landscape at the intersection between positivity bounds and swampland conjectures. Please, 1 hour, Alessia.
Yeah, thanks, Irina, for the introduction, and thanks to all the organizers for inviting me. Okay, I'll talk about this topic that is really at the intersection between the different approaches to quantum gravity and to some extent different fields, including effective field theory. And the reason is that at the basis of the quantum gravity conundrum, so this incompatibility between general relativity and quantum field theory, there are in principle different solutions. And the different solutions in terms of different approaches to quantum gravity, from string theory, loop quantum gravity, asymptotically safe gravity, causal dynamical triangulations, they are all based on different framework and approach the problem of quantum gravity in different ways. But at the same time, the goals that we share are similar. And these goals are testing whether our theories are consistent in terms of their renormalizability, unitarity, and of course, compatibility with the physics of our universe, what we observe at large scales. And we also would like to make predictions in terms of quantum cosmology, quantum black holes, scattering amplitudes, and so on and so forth. And ideally, it would also be a goal to compare the predictions of different approaches to quantum gravity. But all of these goals are very difficult because also these theories speak different languages. They are written in different frameworks, and therefore comparing different approaches is not always possible, especially if we focus on ultraviolet physics. And testing the consistency of these theories in terms of unitarity, normalizability, and so on and so forth is not always possible right away because of the different frameworks that are some of them beyond quantum field theory, so also beyond the Lagrangian descriptions of the theory. And perhaps one approach that could be useful in reconnecting to constraints like normalizability, unitarity, and scattering amplitudes would be that of reconnecting to the framework of effective field theory. And this connection, so from fundamental quantum gravity to the predictions of the theory in terms of effective field theory, is something that one can do, for instance, using by mapping UV predictions into infrared physics. And one approach to this is the swampland program. So for those of you who have been in the business of quantum gravity for a long time, you surely have seen this picture that is popular in the string community. So here, this picture is taken from the review by Ron Palti, and what we have is the energy scale, so how the theory depends on the momentum or the energy scale of the system, and the space of all possible theories. in general, there could be several different effective field theories or effective actions that are consistent on their own, so matter effective field theories that are consistent, but not all of them will be compatible with an ultraviolet completion of gravity. And the idea of the swampland program of string theory, independent of the specific approach that is used, is exactly that of identifying the so-called landscape of effective field theory, the string landscape of effective field theory, which are compatible with an ultraviolet completion of gravity, of quantum gravity. And in the case of string theory, this ultraviolet completion is given by some string theory. And the way this is done within the swampland program, since of course it's very difficult to reconnect ultraviolet physics with the landscape of all of these effective field theories, is to look for arguments and universal patterns in different string models, and identify what is called swampland criteria or swampland constraints that tell exactly what type of theories in the swampland can belong to the landscape. And many of these criteria are inspired by string theory, but others rely on more general considerations that come from black hole physics and effective field theory. Whether these conjectures indeed identify the string landscape, so theories, effective field theories that come from string theory, or more generally a landscape of effective field theories that are consistent, is somewhat an open question. But now the question that I'm asking myself and that I also would like to ask you is whether this picture has a deeper meaning, whether this can be generalized and extended to other approaches to quantum gravity. And precisely the picture that I have in mind is something like this. So instead of having only one possible ultraviolet completion, that is string theory, perhaps there can be different ones. And here in this picture, I'm only representing another one that I'm denoting by AS, so asymptotically safe gravity. But here you can add as many as you want for every approach to quantum gravity that you would like to look at. And then one can think about the dependence of the theory with respect to the energy scale, and so map once again ultraviolet physics into infrared predictions. So one would not only have in the swampland of all effective field theory only the string landscape, but also an asymptotic safety landscape and perhaps others from other approaches. And there will be also some set of theories that are compatible with constraints with theoretical consistency constraints, such as positivity bounds, but also with observations. And of course, there is also the possibility that some ultraviolet completions are not independent, but they are subcases or low energy approximations of others. So for instance, asymptotic safety may be realized in the form of a so-called effective asymptotic safety, so as a low energy approximation of string theory, or other theories could do the same. And now there are different parts of these pictures that need to be understood somewhat independently, and others that lie at the intersection between each part of this picture. So for instance, part of the string community focuses on understanding the fundamental properties, so fundamental features of string theory, so dualities between different realizations of string theory and theory. And the swampland program instead focuses on understanding what is inside the string landscape. Then there is the EST community that focuses on understanding what are the theoretical consistency constraints on the effective field theories in the IR, so that are compatible with locality, unitarity, causality, and so on and so forth. And as for the asymptotic safety community, a major focus has been in the past decades that of corroborating the existence of an ultraviolet fixed point of the normalization group flow, which could serve as an ultraviolet completion and could make the theory non-perturbatively renormalizable. And less of the focus has gone into understanding what is the entire landscape of effective field theories that could stem from such an ultraviolet completion. And understanding this landscape is the big focus on this talk. But while in this picture I've shown only string theory and asymptotic safety, of course this can be, or maybe with some effort, generalized to other approaches. So one could have different ultraviolet completions and then think of a space of all possible effective actions, and then go on with a swampland program that tells us what is the string landscape, and then try to understand what is the asymptotically safe landscape and the landscape of loop quantum gravity as well, and continue like this with all of your favorite theories. And in this, of course, is also important to take into account what are the sets of theoretical consistency constraints and observational constraints. And there is a lot of physics. There are many interesting questions that lie in at the intersections between these sets. And in particular, these involve the consistency of the different theories. So for instance, whether they are compatible with positivity bounds of effective field theory. There is the question about the generality of swampland constraints and the so-called string universality. So the idea or the conjecture is that all consistent quantum gravity theories are part of the string landscape. But this has been tested using string models, not using other quantum gravity models. And it would be interesting to understand whether the infrared of some other consistent quantum gravity theories also lie in the so-called string landscape. So in a sense, whether these swampland conjectures can be more general than effective field theories stemming from string theory. So if they are just consistent theories stemming from quantum gravity. And I see a question by Philip.
Yes. Could you go back to the slide one before?
Okay, so
Yes.
here.
Now, you see the stringy landscape overlaps with the consistent EFTs in one very small region.
That is just, I mean, I'm not saying that there is a small intersection, so that has to be tested.
You're not claiming that
No.
that it's been established that there's an intersection.
No. I'm saying that there are these presets, and they could be disjoint, they could be overlapping, they could have a non-trivial intersections, and this is exactly the question that I'm asking. What are the intersections between these sets?
Okay, so this picture is really the program rather than the result.
Yes, this is just understanding the big picture.
Yes, okay, thank you.
And indeed, understanding this intersection will tell us about the consistency, about the generality of swampland constraints, but one could also infer something about the connections or fundamental incompatibilities between the different approaches. So in principle, different approaches to quantum gravity, so if we just compare them in the ultraviolet, maybe they look very different. But if they would give rise to exactly the same physical predictions, so if the two landscapes from quantum gravity would perfectly overlap, then they could be seen as two different mathematical descriptions of the same physics. So this understanding the landscapes would also tell us about these potential connections. And of course, it would make it easier to connect with observations if we have some actions, some Wilson coefficients that we can look at. So now this would be the general picture for different approaches to quantum gravity, but the focus of my research is mostly asymptotically safe gravity. So let me tell you a little bit more about how this program would be practically implementable in asymptotic safety. So how landscapes in asymptotically safe gravity would be computed. But before going into the details, assuming that not everyone in the audience knows about asymptotically safe gravity, let me just tell you what the concept is. And the concept of asymptotic safety is a non-perturbative generalization of the concept of asymptotic freedom that we know from quantum chromodynamics. So in quantum field theory, couplings may depend in general on the energy scale of a scattering process. And in the case of the strong coupling, the running of the coupling goes to zero as the energy goes to infinity. Or in other words, if one looks at the space of couplings, this means that the theory approaches the origin of the theory space, the free theory, which is also called Gaussian fixed point. But there is another way that the trajectories at high energy may be prevented from diverging, and this is the concept of asymptotic safety. So the trajectories could approach a finite but non-zero value. So in the theory space, this would be an interacting fixed point called a non-Gaussian fixed point. And the idea of asymptotically safe gravity and the asymptotic safety conjecture is indeed that gravity may be consistent within a quantum field theory framework, and that could be non-perturbatively renormalizable if the renormalization group flow attains such a non-trivial fixed point at high energy. And there are different ways to test this conjecture, and these include lattice-like computations, and this is within the so-called causal or Euclidean dynamical triangulation program. And there are the semi-analytical computations of the exact or functional renormalization group, which is what the asymptotic safety community mostly focuses on. And now let me also tell you about a little bit about the functional normalization group, since this is the tool that I'm also going to use in this talk. And in particular, the idea is that of introducing a regularization at the level of the path integral, and then translate the path integral in an integral functional differential equation for a scale-dependent version of the effective action. This is the equation that has been advanced in the 90s, first by Wetterich for scalar field theories, and then by Martin Reuter for gravity. And you don't need really to understand the details of this equation. So the only thing that you need to know is that the left-hand side is just the variation of the action in the space, in principle, of infinitely many interaction couplings, and that the running with respect to this renormalization group scale is generated by a regulated version of the k-dependent inverse propagator. And what this equation does is to generate a flow in the space of theories from the ultraviolet to the infrared, where in particular the ultraviolet tells us about possible ultraviolet completions of the theory, and in particular its fixed points. Every fixed point is a different ultraviolet completion, And every fixed point has its own number of relevant directions. And is attached, of course, with one specific direction. And as one, at the level of the path integral, integrates out fast fluctuating modes, one generates this k-dependent effective action with all terms that are compatible with symmetry and field content of the theory. And in the limit, as k goes to 0, one recovers the ordinary effective action, which in principle could have as many operators as are compatible with the symmetry of the theory, but they would only be parameterized by n free parameters that are exactly the n relevant directions of the fixed point, modulo 1 that fixes the scale of the system. And in particular, the effective action, so the set of Wilson coefficients that are generated by the flow, is important because it gives us access to scattering amplitudes, fully dressed scattering amplitudes, and those observables. So now, how do we translate this picture, in landscapes? And so now let's look again at our picture. We want to start from our fixed point, go down with energy and compute this landscape. The landscape is essentially the set of all Wilson coefficients that come from renormalization group trajectories that are ultraviolet complete. And the landscape is defined in the space of all possible couplings. And this is what I'm representing here. So you can have a theory with 1, 2, 3, 4, 100 couplings, depending on what you are looking at. And the beta functions for this coupling will give you information about the normalization group flow, and in particular about the fixed points of the theory that could be one or could be many. Now, in this example that I'm sketching here, there is one ultraviolet fixed point. And ultraviolet fixed point typically means that it is a saddle point, so it is not fully attractive for all possible trajectories. There can still be trajectories that are not ultraviolet complete because they don't belong to the UV critical surface of the fixed point. And then there are some trajectories that are ultraviolet complete with respect to a fixed point. And then one can follow their flow towards the IR. And in the limit as the renormalization group scale goes to 0, this is exactly what identifies this line, the asymptotic safety landscape. So the asymptotic safety landscape is the set of IR infrared points of all ultraviolet complete renormalization group trajectories. And so it is identified by solving the beta functions for UV complete trajectories for several different initial conditions. And so this also tells us what is the precise recipe to compute the asymptotic safety landscape, and whether this is generalizable to other approaches. It may be possible, maybe a little bit more complicated in the case of discrete approaches, but the recipe should be extendable, perhaps even to non-Lagrangian theories. So in the case of asymptotically safe gravity, what one would do is to start from one specific model, or more technically from a truncation of the action, then run the Farnsworth normalization group machinery to compute the beta functions. And the beta functions at that point could be solved for a sample of ultraviolet complete trajectories. And then the IR limit of these trajectories would identify the asymptotic safety landscape in terms of Wilson coefficients. And then one can use exactly the same Wilson coefficients to parameterize regions that are allowed either by effective field theory or by string theory in terms of swampland conjectures, or by other quantum gravity approaches, or by observations, and then find the intersections. And finding this intersection is really the key to answer the questions that I have presented at the beginning. So now we have a clear recipe, and therefore we can perhaps go to some examples. Okay, I forgot that actually there is also another caveat in defining the Wilson coefficients. So precisely the Wilson coefficients from the function normalization group would be given by the limit as the normalization group scale goes to 0 of the running in principle dimensionful couplings. But in practice, in our IR physics, we can only measure dimensionless quantities. We can only measure ratios between dimensionful quantities, if you like. So one of the dimensionful couplings of our theory, for instance, the Newton coupling, may be used as the unit scale of the system, and then the landscape in the infrared would be parameterized by n-1 dimensionless Wilson coefficients, where n is the number of relevant directions of the given fixed point. So here, the dimensionless Wilson coefficient would be given by the limit as the normalization group scale goes to 0 of the dimensionful running coupling times appropriate scalings of the running Planck mass, which is essentially given by the Newton coupling. But there are, of course, some caveats in this definition, especially in non-trivial situations. So first of all, the function normalization group equation and the function normalization group computations in general are done in a Euclidean signature. And so one at the end of the computations, one needs to decrotate back to Lorentzian in order to compare the predictions with stuff like swampland conjectures or positivity bounds. But at the same time, there starts to be some small evidence that things in Lorentzian signature may look the same in asymptotic safety. Philip, you have a question?
Yes, it's a very quick comment. I've been looking at second order plus fourth order theories, and in those cases, the Wick rotation fails. Namely, if the Euclidean is finite, the Lorentzian is not finite, because the Wick rotation itself introduces an infinity because of its own circle at infinity. So that's just a comment.
Okay. Yeah, this may depend on the specific approach that you use. It's not that things would look the same in Euclidean and the Lorentzian in all possible approaches. What I'm saying that is that in asymptotically safe gravity, where we use the function normalization group computations, so there starts to be some evidence. So there are now a couple of papers with almost Lorentzian and the Lorentzian signatures where we see that the results are essentially the same.
Okay.
And so I'm using this assumption for those talks that what I'm going to present will look the same in Lorentzian signature. The second caveat is about the definition of the Wilson coefficients. When in the infrared there is a logarithmic rounding of couplings, and this of course can happen in the theories, in gravitational theories or in general theories where one has massless degrees of freedom. And then if there is a logarithmic rounding, this introduces actually an ambiguity in how one defines Wilson coefficients. And the reason is the following. So if you think that you have a dimensionless or dimensionful, doesn't really matter, Wilson coefficient here that is given by one constant part, and the constant part in principle is what we can call Wilson coefficient, not the k, the rounding part. And then we have a logarithmic rounding. Of course, in the limit k that goes to 0, this is not well defined. So we can only look at the constant part of the Wilson coefficient. But now I can always add and remove the log with respect to another reference scale aside from different than the Planck mass, and then redefine both A and B. And since what is properly called the Wilson coefficient is the constant part of the form factor, then essentially there is an ambiguity in when there is logarithmic running in how one defines the Wilson coefficient. And therefore one needs a prescription for that. And in particular, the prescription that I used in this paper and that we are also going to use in our upcoming paper is to use essentially the Planck mass to define the logarithmic rounding. Okay, and at this point, so having clarified how, yes.
I would like to ask a question regarding, so at some point you show the figure of the landscapes, and you were showing two types of philosophy for asymptotically safe gravity. One is the one where the existence of an interactive fixed point is really like a principle to define a UV complete theory. And the other one was when you see asymptotically safe gravity as an effective field theory coming from maybe string theory. Okay. And so in this case, what does it mean? So in this basically left case where you speak of effective field theory, basically the existence of an interactive fixed point in this case is not a fundamental requirement anymore. So it should be something derived coming from something else.
Yeah. So so what I mean here, so this is effective asymptotic safety. So there would still be an ultraviolet fixed point in the space of couplings in the regime where quantum field theory holds. Now assume that beyond a certain scale, say the string scale or loop quantum gravity scale, I don't know, there is quantum field theory stops to make sense, stops to be reliable. Then the framework would then be replaced by something else. But it is conceivable to assume that in the regime where quantum field theory works, one would still, the theory would still very well be approximated by the normalization group flow that connects the region close to the asymptotic safety fixed point to the infrared. And the reason is that at least within the approximations that have been used, there are trajectories that connect this ultraviolet completion to the general relativity regime. And precisely the Newton coupling, cosmological constant, and coupling to R squared that one observes. And therefore, even if there would be a framework, something beyond the quantum field theory, in the regime where I can trust the quantum field theory, there would still be these trajectories going close to the fixed point. And if you are close enough to the fixed point, or even starting from the fixed point, which is generated by some phase transition to second order phase transition to a regime where there are different degrees of freedom, then you could still inherit at the level of the quantum field theory the same predictive power of asymptotic safety, but at an effective level.
Okay. And do I understand correctly that the fixed point is always reached at infinite energy? Like,
I mean, you would never really reach
no, I mean mathematically, let's say, the way you define it.
Mathematically, yes. Mathematically, yes.
Yeah, my question was like, if you define the point at infinite energy, which means that you are really going into the deep UV, you are somehow saying that you will trust quantum field theory at this very high energy scale. And at some point I would say, okay, you are basically at infinite energy, you don't need anything else above the energy scale. But what you're saying is that
however, so if you look okay, let me see if I have, okay, so if you look at something like this, so what is like the rounding with respect to a normalization group scale, so the you only actually are at the fixed point at k infinity. So here you are extremely close, but not really there. And there will be a transition scale, like somewhere here, where you step out of the fixed point regime and you go to the general relativity regime. And the transition scale most probably is the Planck mass scale. But beyond that, even if you are not at the fixed point and you are relatively close to it, you are still like in this sort of flat regime of the running. So it is still possible that you are still like close to the fixed point beyond the Planck scale or something around there. And then at some point here, even if you are close to the fixed point, then your quantum field theory fails to describe our universe, and then you have something else.
Okay, no, I see the point. Thanks.
Okay. Okay, and having defined what how one can define landscapes in asymptotic safety and the corresponding Wilson coefficients, let's go to practical computations and examples. And the first one is asymptotic safety landscapes in one loop quadratic gravity and their interface with some swampland constraints. So the question is how general these swampland constraints are and whether the string landscape has some intersections with the asymptotic safety landscape. So now the toy model that one starts with is quadratic gravity at one loop. So one has the standard Einstein-Hilbert action plus corrections at quadratic order, so C square, R square, and Gauss-Bonnet term. And here we can identify three dimensionless Wilson coefficients, plus the Gauss-Bonnet, but in the case of one loop approximation, well, in general, the Gauss-Bonnet term is essentially decoupled from the flow, so it is not really important for the argument. But we also have a one-dimensional full scale, which is the Newton coupling, or the Planck mass equivalently, and therefore we can define three physical quantities, three dimensionless quantities that are g times lambda, that is essentially the cosmological constant in the Planck units. And then these two ratios, gr, which is essentially the coupling to r square, and gc, which is the coupling to c square. And here we did not compute new beta functions. We just took them from one paper by Codello and Percaccio, 2006. And in this case, there are two non-trivial fixed points at these values for decouplings, and the beta functions are actually pretty simple at one loop, so it is kind of easy to compute the flow. The idea, once again, is to start from the ultraviolet fixed point, run the normalization group flow by stepping a little bit outside of the ultraviolet fixed point, and then go towards the IR along relevant directions, just that we know that we are on ultraviolet complete trajectories. And then do this for several different initial conditions and identify the landscape. And this is precisely what we did. And we did that for by integrating the normalization group flow for essentially 10 million different initial conditions. And what I'm representing here is exactly the landscape, or the points, these infrared points that belong to the landscape. They are the blue points in the space of the three dimensionless Wilson coefficients that I'm interested in. So GC, the GR, and G lambda. And it turns out, and this is somewhat surprising, I don't yet have an explanation for this, they all lie on a plane. And in particular, we could extract the equation for this plane And this is given by this equation where omega lambda is just one of the 6-point values that I have shown. And in particular, and this is important, GC is positive always for the infrared points of the asymptotic safety landscape. So at this point, we have our asymptotic safety landscape, and we want to compare it with some of the swampland conjectures. And in particular, the swampland conjectures that we used are the weak gravity conjecture, the sitter, and the Transplanckian conjectures. Starting from the weak gravity conjecture, so the brief, it says that in a consistent quantum field theory of gravity coupled to a U1 theory, there must be at least one state whose mass in Planck units is approximately smaller than its charge. And this essentially ensures that the quantum field, so that the effective field theory is consistent and black holes remain sub-extremal. But in particular, this condition is corrected once one introduces, in particular, this condition about the extremality is corrected by higher derivative corrections. And this has been seen in different papers using different methods. And essentially, the extremality conditions is changed by a factor delta, which depends precisely on these coefficients, the couplings to R square, R minus square, and Riemann square, and also on psi, which is related to the ratio between a black hole charge and its mass. And it turns out, if one translates this condition, so with this Ci to our Wilson coefficients, the validity of the weak gravity conjecture that holds for when this delta is positive is precisely fulfilled by the asymptotic safety landscape, since GC has to be positive. All the asymptotic safety landscape lies at GC, bigger than 0. The second conjecture is, or the other two conjectures that we considered are the de Sitter and the Transplanckian conjectures that are essentially, one is a particular case for the other. And this is about the compatibility of scalar field theories with ultraviolet complete theories of gravity. And it states that the potential as always for a scalar field has always to be bounded by its variation, and this has to happen for field range smaller than the Planck mass times some constant. So F and C here are constants of order 1. So I mean, this is a little bit unsettled, so it could be 1, it could be 100. These conditions have to hold. So we verify them for different values of F and C. And in particular, the Transplanckian conjecture holds for one specific value of C, which depends on the space-time dimension. In our case, D is equal to 4. And this translates to non-trivial constraints in our case, because the scalar degrees of freedom that we have are essentially those attached with the scalar degree of freedom of coming from R square. So in our case, the potential V is a Starobinsky-like potential, which depends on the cosmological constant and on the inflaton mass m square, which is directly related to GR, so the coupling to R square. And for different values of F and C, one also gets different and non-trivial bounds on our Wilson coefficients. And here I'm showing these bounds in two different cases. So if this is, of course, I mean, note that this is independent of GC. It only depends on GR and lambda. So this is why here I'm showing these two plots in the GR, G lambda planes. And the two hold for different values of C in this range for both. And the left corresponds to f equal to 0.1 and the right to another value of f. And the colorful regions are the regions where the sitter and the Transplanckian conjectures are satisfied. And there are also white regions where they are not satisfied. And in particular, it turns out that the asymptotic safety landscape can be in this region. So these two conjectures can be violated in asymptotic safety. And this is now what I'm going to show in the next slide. And in the next slide, you should be aware that, so what I'm going to do is to translate these two-dimensional plots in 3D. And the two should hold for every value of GC. So the two will become three-dimensional, but keeping the same shape. And so this is all together. The asymptotic safety landscape, that is the plane that I've shown you a few slides ago, is given by this equation, and is exactly this green plane that I'm showing you in different with different angles to grab the picture that I'm trying to that appears. The easy one, the other easy one to understand is the weak gravity conjecture, since it simply corresponds to positive GC. So it is just this yellow part of this hypercube, and it just corresponds to GC bigger than 0. And of course, the asymptotic safety landscape is fully inside this region, while the sitter conjecture and the Transplanckian conjecture have a non-trivial shape, because it is these hyperboloids that define the regions of compatibility, and these hyperboloids are valid for every GC. So, and this goes in the vertical direction. So essentially they cross the asymptotic safety landscape, and at the end of the day, what one has is a non-trivial intersection between the asymptotic safety and the string landscape. So pointing either to a partial compatibility or to the idea that perhaps we should investigate more in this direction, and in particular with more sophisticated models. And this goes in the direction of this second example that I want to show you, which is a more sophisticated model with more terms and with a full-fledged functional normalization group computation. And here we are going to compare with one swampland conjecture, that is the weak gravity conjecture, as well as positivity bounds. So we have now a starting point, which is a larger set of terms. So with the gravitational part, where in order to minimize actually the complexity of the system, we only focused on the essential couplings. So couplings that cannot be redefined away by field redefinitions. And these are the Einstein-Hilbert term and the Gauss-Bonnet term, plus the part concerning that describes the photon at quadratic order, and a non-minimal coupling between gravity and Q1. And in this system, we can also define the three-dimensionless Wilson coefficients, which are a combination of these couplings, and for a reason that in particular by summing the G2 and the G4, one completely eliminates the logarithmic rounding, so it cancels out. So at least the Wilson coefficients W plus and WC would not be affected by the logarithmic ambiguity in the definition of the Wilson coefficients. But the W minus instead will still have this type of ambiguity. And in this system, one can then compute the beta functions, and I spare you the details that are not very important. And we find two fixed points. One is more predictive than the other. One is comes with only one relevant directions, which is used actually to set the scale of quantum gravity. So in practice, this is a zero parameter theory. The resulting landscape will be 1 point. And the second one comes with 2 relevant directions. For the experts, you can also look at the values of the location of the fixed point and the critical exponents, but this is not very important. The only important thing, the only relevant, the only important information is the number of relevant directions, which coincides with the number of positive critical exponents. And here is 1 positive critical exponent, and here is 2. So in this case, we would have 2 alternative ultraviolet completion and 2 sub-landscape in a sense. So let's now look at these landscapes. Once again, one can run the normalization group machinery for different initial conditions and try to understand what is the geometry of this landscape in the space of couplings identified by the 3 Wilson coefficients.
Sorry, Alessia, there is a in the chat.
Oh, okay. Let me see if I can open it too.
Is this asymptotically safe model ghost-free?
Yes, this one, yes, because you don't have the R² part of the action. Essentially, by removing the inessential couplings that are can anyway be redefined away by field redefinition, one can just get rid of fictitious ghosts. And from complete computations that also involve the R² operator, we see that the dressed propagator is also free from ghosts. So essentially, it doesn't really make a difference whether one includes the R² operators or not. Okay, and at this point also, since I think I have the last 5 minutes, I would now show these landscapes that come from these 2 fixed points. And here I'm denoting the landscape from the first fixed point with a red dot. It is 1 single point because we have only 1 relevant direction, so which is used to set the scale of quantum gravity with the Planck scale. And once you do that, the landscape is made of 1 single theory. And this is exactly represented by this point. And the second landscape is represented by these points in the IR, and it is almost a straight line. Almost, but the part close to the second sub-landscape, where there is a small candy cane regime which connects the 2 sub-landscapes. So if one zooms in, we have exactly this type of shape where the sub-landscape from the fixed point 2 bends to connect with the fixed point, with the landscape from the fixed point 1. And at this point, let me also, so for the sake of comparison with positivity bounds in the different regimes, let's also introduce some important nomenclature that I found interesting from Google. Apparently, there is nomenclature on how one calls different parts of a candy cane, and in particular the curved part. This part is called the warble, and the straight part is called the straight, which I did not know. And this part corresponds to different regimes, actually, of the asymptotic safety landscape, which have different properties in terms of comparing with positivity bounds. So I'm going to show this now. But before that, let me quickly summarize which kind of bounds we looked at. And in particular, we looked at bounds which translated in our couplings look like this. They are taken from this paper, and also the electric weak gravity conjecture in the presence of higher derivatives looks very similar to one of the positivity bounds, aside from the absence of an absolute failure. And the idea is exactly to compare with these positivity bounds, but still keep in mind, and I've already told you about this, there is a caveat in how one defines the one of the Wilson coefficients because of the log running in the infrared. And there is actually also an expectation that once gravity is turned on, standard positivity bounds, so something like this, can be violated by small amounts, which is suppressed by some powers of either the Planck mass or a cutoff scale appearing in the effective field theory. But in our case, we only have the Planck mass as a scale of the system. So we would expect something like this. And this is exactly what one gets out of the computation. So when comparing these two combined to landscape with the region which is allowed by positivity bounds and with gravity conjecture, and this is all in Planck units, one sees that one is slightly outside of the region. So in particular, when one looks at the violation in Planck units as a function of the landscape, where the right part corresponds exactly to this sub-landscape one, and this part of the plot corresponds to going away from the most predictive landscape. Then you see that there are indeed the violations of positivity bounds, but these are numbers in Planck units. So essentially, in the stable part of the landscape, the violation gets larger, while in the warble, so that corresponds to this part that is close to the most predictive landscape, then the violation is minimized by, and it is a Planck scale, strongly Planck scale suppressed. And this is indeed compatible with the expectations from effective field theory that once one turns on gravity, but in particular the bit that is important is that one introduces massless degrees of freedom, and standard positivity bounds are derived when no massless degrees of freedom are there. And when this happens, then positivity bounds can be slightly violated, and the violation is suppressed by the scales of the system. And this brings me to my conclusions. I think we are approximately on time. And I believe that computing quantum landscaping, different approaches to quantum gravity, either by using arguments such as swampland conjectures or practical computations to define this set of effective field theory is extremely important, as one can access different physical questions and important questions like about the generality of swampland conjectures, about the consistency of different quantum gravity predictions, about the comparison between approaches and their potential connections. And in the case of asymptotic safety, we have a clear recipe to do this, because it is exactly the recipe of the functional normalization group that allows one to compute Wilson coefficients and then compare them with swampland conjectures, positivity bounds, observational constraints, and so on and so forth. And I've shown you that two different examples of this. One is the case of one loop quadratic gravity, and one is a more sophisticated example, which includes terms of quadratic order, both in the gravitational and the U1 sector, and it is a full-fledged functional normalization group computation. And one case shows us that the intersection between the asymptotic safety and the string landscape is non-trivial. So there can be some conjectures that are satisfied, other may be violated in some parts of the landscape. And the second case of study shows us that there can be Planck scale suppress violations of positivity bounds, but in particular there is one, as expected from effective field theory considerations, but there is one fixed point, the one corresponding to a zero parameter theory, which corresponds to a landscape that is made of one point where the violation is minimal. And if I have to pinpoint one common feature between these two computations, it is this near flatness of the asymptotic safety landscape, which is somewhat unexpected. And it is non-trivial that out of a renormalization group computation and taking the infrared limit, one gets infrared points that all lie on a surface which is nearly flat modulo this warble that connects the two sub-landscapes. And whether this is a coincidence or a universal pattern in asymptotic safety is probably to be understood. And this may have implications and fundamental explanations that at the moment are unclear to me. And with this, I said everything that I wanted to tell you today. So I thank you for your attention, and I'm looking forward to questions.
Okay, thank you very much for your very interesting talk with very, very nice pictures that make simplify us to understanding your claims. Question, please.
Well, I have quite a few, but I'd like other people to have the opportunity first.
But okay, we can start.
All right. So, Alessia, first of all, thank you for this very nice talk. Going back to this basic equation, the functional relation of Wetterich, has that ever been established outside of a renormalizable theory?
So what do you mean exactly? I mean, the question is independent of whether the theory is renormalizable. So the idea is just to start from the path integral of a general theory, and then translate that in this equation. And in this translation, you are not really assuming anything about the renormalizability of the theory.
Okay. But the renormalizability, I think, comes in the question of whether the trace over an infinite number of degrees of freedom is finite.
I mean, of course, whether the stuff is finite depends on the values of decouplings and depends on the normalization group scale. And the statement about renormalizability, so whether this equation is well defined, is whether on some normalization group trajectories in the ultraviolet limit, whether they diverge or whether they attain fixed points. Of course, if they diverge, they may make this right-hand side well-defined.
Okay, well,
but you can still study this.
I mean, let me ask the question completely in reverse. Mm-hmm. Why do we ever need renormalizable theories?
Because then you, without a normalizable theory, you cannot make predictions.
Well, I mean, I cannot, or we haven't succeeded. It would seem that if I can use this equation of Wetterich and Reuter for a non-renormalizable theory, and if there is a fixed point, I can get you claim I can get sensible answers, and those answers should in the end lead to predictions, which may or may not work. But I don't think that it would prevent me from getting predictions.
The point is, if a theory is so the existence of a fixed point and the fact that a renormalization group trajectory is complete with respect to the fixed point is a statement about renormalizability. So fixed points, the existence of fixed points tells you that some trajectories, some theories will be renormalizable. if they have at least one relevant direction.
Okay. The other question I had was in your second model, which involved F mu nu squared. That's it. The only other gravity piece is the Gauss-Bonnet term. So in a sense, you're saying is that this rather strange electromagnetic interaction can basically stabilize Einstein gravity, which is an interesting point in and of itself, if that's...
So you have also the non-trivial...
you put in the biotech.
Coupling.
Yes.
You also have a non-minimal coupling between the one and the gravity, and you have the Gauss-Bonnet term.
Okay, good.
And actually, if you just take the Einstein-Hilbert truncation and you do a computation with that, you would still see a fixed point. So you would see that the theory may be not perturbatively renormalizable. But the point is, if you stop at the Einstein-Hilbert truncation, you don't know if that fixed point is just an artifact of your very peculiar action or whether it is there. And in order to check that, you have to go higher order in the action, in the variance in the action.
Okay, good. Oh, thank you.
More questions, please?
Alessia, may I ask you a question? It's Alexei.
Of course.
Look, actually, I didn't get explicit exactly. What do you mean when you say that these extra possible degrees of freedom are inessential?
So, inessential for a coupling, not for a degree of freedom, means that you can redefine it away via field redefinition. Okay, and that's of course provided that you are not removing degrees of freedom. Okay, but the point is,
did you try to do this?
yes.
I mean, how does it work?
So the way this goes a little bit in the technical direction. So what we used to do this is not a plain functional normalization group, but something called essential functional normalization group that is really set up to do these field redefinitions once you know what the degrees of freedom of your theory are. And this is an information that we can get from full-fledged functional normalization group computation, so where you also have R-squared terms. And there you see that in the spectrum of the full theory, at least to the approximations that one has seen so far, there aren't ghost degrees of freedom. And this would indicate that the graviton is the only thing that you have in there. And so a posteriori, you can use this essential version of the normalization group, which allows you to eliminate the couplings that are inessential once you have made sure that there isn't an additional degree of freedom.
Okay.
Okay, thank you.
More questions, please? If no questions, maybe I will ask some general question. As I understand, you working mainly in 4-dimensional case. Have you tried some ideas similar what you try to develop, for example, in framework on one of a D-dimensional approximation? Because I like to have some systematic perturbation theory, not just saying saying, let's take some particular graph or so on. Have you tried something
No,
within
not
one
really.
of the expansion? Maybe also you can simplify your consideration in three-dimensional case, for example.
Yeah, I mean, that is a good suggestion for something to do in the future, but so far we didn't look at that because, I mean, our focus was computing the landscape for asymptotic safety, and so we assumed 4 space-time dimensions, which is the starting point in asymptotic safety. And considering models with different dimensions, of course, could make sense, like for computational purposes, like to understand how this thing of computing landscapes goes. But in asymptotic safety, we to be compatible with what you observe to date, we fix D to be 4.
I see. Oh, thank you. More questions, please. If no more, okay, let me wait 1 minute. Maybe people would like to ask more. And also some general questions. Do you think if you consider supersymmetrical model, does matter would be simple? What do you think in principle?
No, things would be more complicated because in
no compensation of some diagram or something like that.
I think things would get more involved, but I have never worked on supersymmetric models.
I see. Thank you.
Maybe I can ask a quick question.
Please.
But I think one of the main point of your approach is that at some point you would like to discriminate between quantum gravity approaches, right? For instance, between string theory and asymptotically safe quantum gravity. But at the moment, can you say anything about the possibility to discriminate with the current understanding of this, like
so I would say,
constraints?
So comparing the two other approaches other than string theory depends on whether those communities will make an effort to compute landscapes. So it's difficult to say in that direction, but some comparison with string theory may be possible. And of course, there is one assumption that goes in there, namely that the swampland conjectures identify indeed the string landscape, and that they are all not conjectures, but trustable criteria that identify the string landscape. Under that assumption, one can start making some connections with asymptotic safety. So it seems that the weak gravity conjecture, to some extent, is compatible with asymptotic safety, modulo maybe Planck scale suppressed violations. But the sitter and the Transplanckian conjectures are not. So in asymptotic safety, we can have stable de Sitter solutions. So there are regions of the landscape where there is none, but there are also regions where there are some solutions.
So somehow
still compatible in some region of having non-trivial. So maybe there may be some predictions in common, but at the moment within the approximations that we have looked at, it looks like there isn't a perfect overlap, or it doesn't look like one landscape is inside the other. So it goes in the direction of either they are not compatible, so they are related to each other, or the conjectures that we have seen, in particular the Sitter and the Transplanckian conjectures, are not always verified in string theory, and and this is not impossible because even within the string community there are some conjectures that are well established, like no global symmetry or weak gravity conjecture, and others like the de Sitter conjecture, which is more under debate. So and this is what we have looked at. So I would say that it can the conclusion can go at the moment in two different directions. So either there is something going wrong with some swampland conjectures, or there is no compatibility between asymptotic safety and some part of the string landscape. But these are just two examples. So I think that one should not infer too much from two cases only.
So the second direction would be maybe more interesting, right? Because you can stimulate.
Yes, of course.
Okay, thanks.
Okay. Okay. More questions, please? If there is no more questions, let's thank the speaker again. Thank you very much for your very interesting talk. And let's stop our seminar. Okay.
Thank you, Alessia. Thank you very much.
Thank you.
Thank you very much.
And if you can send in the slides,